through the black emptiness of space, where light takes minutes, hours, even years to travel to far-off worlds, we find ourselves floating in a cosmic sea far bigger than anything we can truly grasp. Every tiny light in the night sky isn't just a place to go, but a clock, quietly counting the space between human wonder and the great mystery. Tonight, we'll float past Earth and travel across millions, even billions of miles, following the quiet paths through space and time. How long would it really take to stand under Venus's golden clouds or see Jupiter's storms with your own eyes? What about Neptune, where one day is longer than our minds can stretch? If you like these trips through time and wonder, please hit like and subscribe to help us go even farther together. Now get comfortable. Let your mind rise and let us float gently out into the waiting darkness. Let's get started. Music in the quiet after launch. Earth starts to slip away below us, not as a planet, but as something remembered. The thunder of engines grows quiet, replaced by the deep hum of space itself. Time slows down. Our journey starts not with movement, but with change from earthbound to cosmic. From the second ignition starts, the world we've always known begins to fade into the back of our minds. The metal shell shakes. The power of millions of pounds of force pushes us up. And in that climb, we're no longer people of a planet. We're travelers of the emptiness. As gravity lets go, Earth's familiar shapes, oceans, mountains, swirling clouds, shrink into one amazing view. It's here in this narrowing view that we feel the first shift in time. Seconds expand, thoughts go deeper. A deep calmness fills our minds, as if the universe itself is taking a soft breath before showing its secrets. As the spacecraft crosses the common line, that invisible edge between Earth and space, everything shifts. The weight of the atmosphere disappears. The sky, once shades of blue, turns into velvet black. There's no sunrise, no sunset, only the slow spin of the planet below us. Every turn, every shadow spreading across continents becomes a reminder of how fast life moves down there and how slowly time seems to pass up here. The hum of instruments takes the place of wind sounds. Movement is now measured not by footsteps or wheels, but by orbit, by momentum, by gravitational forces that reach far beyond anything we felt on Earth. The journey ahead isn't just about distance. It's about letting go of everything human. The need for solid ground, the sense of up and down, the belief that time moves steadily forward. Here, time becomes stretchy. It grows with each mile traveled, each point passed from low Earth orbit to the edge of the planet's gravitational pull. We start to see that space isn't empty, but full of invisible forces. Gravity pulls, light bends, even time itself, like some ancient wanderer, moves differently in these places. As we finish our first orbit, Earth glows below us, peaceful and delicate. The cities that once seemed massive now look like tiny dots of light scattered across the dark side of the globe. The storms that once ruled our weather become slow spirals drifting across continents. Up here, borders fade, nations vanish. There's only one living world, spinning patiently under the hugeness of space. And with this understanding comes the first touch of cosmic humility. Humanity has always been a space-traveling species. We've just been waiting for the technology to remember. As our spacecraft lines up for trans-orbital injection, getting ready to leave Earth's gravity well for the wider solar system, we feel the last pull of home. It's not just gravity, it's emotion. The knowledge that every second going forward will put more distance between us and everything we've ever known. But there's also peace in this moment. The peace of purpose, the peace of curiosity. Beyond Earth lies a heavenly path carved over billions of years by the movements of planets and stars. We're not making this journey, we're following it. With the engines firing again, we're no longer circling Earth. We're leaving it. In this moment, our calendars no longer follow days, but distances. Our clocks no longer count hours, but paths. And as the last glow of Earth's atmosphere fades into the endless night, we finally understand we haven't lost our home. We carry it with us as a memory, a light, and a promise that every mile traveled is a step toward knowing not just where we are in the universe, but who we are. Our voyage has started. Beyond the atmosphere lies a place without resistance, where movement goes on forever and gravity reshapes our path. Here, travel time is measured not in miles, but in speed and slingshots, as planets themselves become stepping stones through time. In space, there are no highways like on Earth, no laid-out roads or visible trails to follow. Instead, we're guided by forces older than time itself: gravity, momentum, and orbital geometry. These invisible currents form pathways that spacecraft must carefully follow, using the gentle pull of planets to speed up, redirect, and push themselves forward. The real art of traveling between planets isn't brute force, but balance. We don't fight against gravity. We use it as a friend, letting it shape our journey like wind fills the sails of a ship crossing a cosmic ocean. These gravity pathways, called transfer orbits, follow exact mathematical curves that connect one planet to the next. They're not chosen for ease, but for efficiency. A spacecraft can't just fire its engines in a straight line through space. It must fall toward where it's going, riding the bends in space-time carved by planetary mass. Earth's gravity holds us in its hold until we reach what scientists call escape velocity, about 11 km/s. Once this limit is crossed, we're no longer tied to Earth. We become wanderers on the solar wind, carried not by fuel, but by the beautiful physics of momentum. Here in the vacuum, motion is persistence. Without air resistance, every small push goes on forever unless stopped by another force. A single burst of power can send a spacecraft coasting for months or years. Every moment becomes a careful balance between time and energy. Go faster, and you must use more fuel. Save fuel, and you must accept that time, days, weeks, years, will stretch into the great space ahead. The planets themselves become heavenly rest stops along our journey. Their huge gravitational fields act like cosmic slingshots, speeding up our spacecraft without using a single drop of fuel. This technique, known as a gravity assist, is both a scientific wonder and a poetic dance. As we get close to a planet, we fall into its gravity. As we swing past, we steal just a tiny bit of the planet's orbital momentum, using it to slingshot outward higher speed. In return, the planet loses a tiny, almost impossible to measure amount of its own motion. Tiny but real, proving that even on a planetary scale, nothing in the universe is free. These invisible highways aren't always open. They exist only in narrow windows of alignment. When two planets orbit into the right positions relative to each other, launch too early or too late, and the pathway closes, we'd have to travel a longer, slower curve, wasting valuable time. In space, timing is everything. Mission planners sometimes spend decades waiting for a perfect moment. A moment when Earth, Mars, Jupiter, and Saturn line up like stepping stones stretched across cosmic waters. As we travel along these gravitational lanes, we're reminded that the universe isn't empty. It's a web of forces, each pulling on the other, each shaping the future of everything in motion. Space isn't a void to be crossed. It's a living landscape, constantly shifting, flowing, and guiding us through pathways that can't be seen, only felt. And so we continue, eyes set not on where we are, but on where gravity will take us next. For to travel through space isn't simply to move. It's to gently give in to the silent design of the universe itself. Mercury waits in the inner dark, a world so close to the sun that dawn comes like a blade of white fire. To reach it, we don't speed up. We give up speed, falling inward along a curve of light. The question isn't just how far Mercury is, but how slowly we can learn to arrive. From Earth's orbit, every instinct says, go faster. But the inner solar system teaches a gentler lesson. To reach Mercury, we must lose energy. Earth circles the sun at about 30 km/s. Mercury whips around it at roughly 47. As we drop sunward, our speed around the sun naturally goes up. So, the real challenge isn't getting to Mercury. It's arriving slow enough to stay. That's why missions to this small burned world use complicated dances of flybys and gravity assists, shaving speed with each pass until capture becomes possible. The fastest way to simply touch Mercury is a direct transfer for a flyby, historically around 3 to 5 months. Mariner 10 proved this in the 1970s, taking about 4 months from launch to its first Mercury encounter. But orbiting Mercury, truly staying there, takes patience. NASA's Messenger spacecraft launched in 2004, looped past Earth once, Venus twice, and Mercury 3 times, finally slipping into orbit in 2011, about 6.5 years after leaving. Europe and Japan's Colombo followed a similarly complex path. 1 Earth flyby, 2 at Venus, then multiple at Mercury, spending years cutting speed before planned orbital insertion in the mid-2020s. Inward isn't closer. Inward is harder. Approach becomes an exercise in calmness. Each flyby is a metronome tick in a long song, a precise brush with a planet's gravity, a quiet course fix, a gradual surrender of energy. Between encounters, the spacecraft coasts through glowing silence, the sun growing bigger, harsher, more demanding. Heat shields become lifelines. Sunlight here is up to 10 times stronger than what warms Earth. Guidance, navigation, and control systems practice a form of heavenly tai chi. Small movements, huge results. And then Mercury fills the window. A charcoal gray world cratered and ancient, framed by a solar glare so fierce it turns space to glass. Temperatures swing from burning to freezing up to 430 degrees C, 800 degrees F at noon, dropping below 170 degrees C, 290 degrees F at night, with almost no atmosphere, only a fragile shell of atoms knocked loose by sunlight and tiny space rocks. There's no wind, no weather, no softening haze. Shadows cut knife-sharp boundaries. The sky is always black. Time on Mercury feels inside out. A year lasts only 88 Earth days, yet one solar day from noon to noon takes 176 Earth days. Stand on the surface near the edge, and you could watch the sun creep, pause, even seem to go backward near its closest point to the sun. A strange dance born of orbital rhythm and rotation. Here, dawn is a geological event. Scientifically, Mercury is a puzzle wrapped in extremes. An oversized iron core, a global magnetic field in a world so small, a surface scarred by volcanic plains and cliff-like features, lobate scarps that show a planet still shrinking as it cools. Each orbit maps a chapter of planetary formation written in metal and light. How long does it take to reach Mercury? For a flyby, just months. For an orbit, years. Patient years spent peeling away speed layer by careful layer. The reward for that patience is a viewpoint unlike any other in the solar system. The innermost fortress of our star where space, heat, and time are distilled to their basic forms. And in that stark brightness, Mercury offers a final lesson. Sometimes the shortest distance takes the longest grace. Venus glows like a lantern in the dawn sky, closer to us than any other planet. Yet reaching, it means dropping into a world of crushing heat and endless storms. How long would it take to glide through its clouds and see a sunrise that never ends? From the surface of Earth, Venus looks peaceful, soft, glowing, almost gentle in its beauty. Ancient stargazers named it after the goddess of love, charmed by its steady brightness. Yet behind that golden glow lies a planet so extreme that it challenges every idea we have about living conditions, air pressure, and time itself. To reach Venus, we must first understand that we're not simply traveling to a neighboring world. We're diving inward toward the furnace of the sun, falling toward a planet that spins to a different beat than any other in the solar system. Although Venus is Earth's closest planetary neighbor, reaching it isn't as simple as pointing a spacecraft straight at it. Because Venus orbits closer to the sun, we must first reduce our speed around the sun, basically falling inward. This takes more energy than traveling outward to Mars. We must carefully time our launch to match Venus's orbital window, which opens roughly every 19 months. When the alignment is perfect, a spacecraft traveling on a Hohmann transfer orbit can reach Venus in about 120 to 150 days. Just 4 to 5 months of drifting across the void, watching the sun grow bigger with each passing day. During the journey, the spacecraft is slowly caught by the sun's gravity, speeding up as it draws closer to the inner solar system. Temperatures climb, radiation levels rise, and our destination grows brighter, changing from a distant star like object to a world covered in thick clouds that bounce nearly all sunlight back into space. This is why Venus shines so brightly. It's not a mirror, yet it reflects more light than any other planet, glowing like a cosmic lighthouse in the early morning and evening skies. Getting close to Venus is like approaching a dream wrapped in mystery. There are no shadows here, only a constant blanket of light filtered through the air. The planet spins so slowly, taking 243 Earth days to complete one rotation, that a single Venusian day is longer than its year. If you stood on its surface, the sun would seem to rise in the west and set in the east, moving across the sky so slowly it would seem almost frozen. Imagine standing on a world where sunrise takes weeks, where time stretches so far that a single afternoon could last a month. Yet, the beauty of Venus hides a punishing reality. Its atmosphere is made almost entirely of carbon dioxide, trapping heat in an unstoppable greenhouse effect. The surface reaches temperatures of nearly 880 degrees F, hot enough to melt lead. The pressure is over 90 times that of Earth, the same as being nearly a mile beneath the ocean. Clouds of sulfuric acid swirl overhead, bouncing sunlight back into space, even as they trap heat below. Once imagined as a lush jungle world, Venus is in truth a planetary warning story. But while landing on Venus may be impossible for humans today, exploring its upper atmosphere could be our key to understanding planetary evolution. At about 50 km above the surface, temperatures and pressures are remarkably Earth-like. It's here in the golden haze that future balloon-like homes could drift peacefully above the inferno below, forever watching the horizon where sunset never truly ends. To reach Venus isn't only to measure distance, it's to step into a mirror of Earth's past and a warning of its possible future. The journey there may take only months, but the discoveries it offers could span centuries of human understanding. Though Venus is Earth's sister in size, its atmosphere is a furnace of carbon dioxide. As we approach, we measure our journey not just in distance, but in the unfolding history of a planet that became a warning. Earth and Venus were born beside each other, shaped from the same ancient dust that circled the baby sun. In their earliest days, they may have sparkled with oceans, clouds, and the building blocks of life. But where Earth calmed, cooled, and nurtured life, Venus spiraled into disaster. As we drop toward Venus, our spacecraft becomes a time machine, following the different paths of two planetary siblings, one that chose balance, and one consumed by runaway change. The deeper we go, the more Venus shows not just its nature, but the delicate fragility of being able to support life itself. From orbit, Venus looks peaceful, its creamy clouds slowly churning in an endless global blanket. Yet, beneath that front lies a world of relentless chaos. The atmosphere is made of over 96% carbon dioxide, with thick layers of sulfuric acid clouds hide the surface from view. The pressure is more than 90 times that of Earth, the same as being nearly a kilometer beneath the ocean. The heat reaches nearly 880 degrees F, 470 degrees C. On Venus, metal melts in the open air. Spacecraft survive only minutes before being crushed or cooked into silence. But Venus may not have always been this way. Some planetary scientists believe it once had oceans, shallow seas that boiled away as volcanic eruptions filled the air with greenhouse gases. Without a stable magnetic field to protect it from solar radiation, Venus slowly lost its water to space. Hydrogen escaped into the void, while oxygen reacted with surface minerals, leaving behind a desert of superheated rock. Venus didn't die in a sudden disaster. It changed slowly, inevitably over millions of years, proving that planets, like living things, can age and break down. The winds in Venus's upper atmosphere travel at hurricane speeds, circling the planet in just 4 Earth days. This event, known as superrotation, causes the clouds to race endlessly around the globe, driven by heat so intense that the very air seems to churn with desperation. Lightning flashes within the toxic storms. Acid rain forms in the clouds only to evaporate before it ever reaches the ground. Even the word rain loses meaning on Venus. What falls from the sky never touches the surface. As we imagine what a human explorer would experience, we find that a step onto Venus would be a step into a furnace. The skies would be an unbroken orange haze. The horizon would shimmer with distortion from the burning heat. There would be no blue sky, no stars, only darkness and the distant shape of volcanic plains. Venus is home to more volcanoes than any other planet, perhaps over 1,600 major ones, many still thought to be active. It's not just hot. It's alive with internal fire constantly reshaping its surface. Yet among this hostility lies a deeper truth. Venus isn't just a failed planet. It's a mirror showing us what can happen when a delicate balance breaks. The same greenhouse effect that warms Earth to life has gone unchecked here, turning paradise into hell. In studying Venus, scientists gain insight into Earth's future. Venus isn't our enemy. It's our warning. If life ever flickered here, it's gone now, erased by the relentless grip of heat and pressure. Venus is a reminder that being able to support life isn't guaranteed, that a planet's fate is written not just in what it's made of, but in its delicate relationship with its star. The time it takes to reach Venus is measured in months, but the time it takes to understand it may span generations. As we leave its orbit, we do so with a sense of respectful caution, aware that in Venus we've glimpsed a possible destiny we must try to avoid. Mars calls with its rusted deserts and whispering dust storms. Visible even to ancient eyes, the red planet holds our dreams of colonization. But how long until human boots leave the first footprints in its ancient sands? For centuries, Mars has called to us across the darkness, its red glow a constant reminder that another world lies just within our reach. Unlike Venus, which hides itself in secrecy, Mars offers its surface plainly to the cosmos, inviting us to study its canyons, valleys, and frozen polar caps. It's not just a planet. It's a possibility, a world that might one day hold human life beyond Earth. To journey to Mars is to journey into our own future, a future where life becomes interplanetary. But Mars isn't an easy neighbor to visit. Its orbit around the Sun is elliptical, sometimes bringing it within 34 million miles of Earth, and at other times distancing it by more than 250 million miles. We can't choose to leave whenever we want. Our departure must line up with a cosmic rhythm known as the launch window, a moment that happens roughly every 26 months when Earth and Mars align on the same side of the Sun. In this narrow corridor of opportunity, the journey is fastest and needs the least fuel. When conditions are ideal, a spacecraft traveling on a Hohmann transfer orbit can reach Mars in approximately 6 to 9 months. This isn't a straight path, but an elegant curve through the solar system, using Earth's momentum to carry the spacecraft outward until Mars's gravity catches it. During this time, astronauts would spend more than half a year drifting through deep space, farther from home than any human has ever traveled. Day by day, Earth would shrink into a pale blue star until it appears no brighter than Venus does from our skies. The mental journey in many ways is greater than the physical one. For the first time in human history, travelers to Mars would watch Earth become just another point of light in the universe. Communications would be delayed by minutes. Time would take on a different meaning, not measured in days or schedules, but in distance from home. Each moment would be accompanied by the knowledge that returning isn't immediate, that every mile forward is a mile deeper into the unknown. As the spacecraft gets close to Mars, the planet gradually grows from a red dot into a glowing sphere. Its rusted plains and ancient riverbeds show themselves through swirling dust storms. The thin atmosphere, less than 1% as dense as Earth's, gives almost no protection from the harsh radiation of the Sun. Yet below that dusty cover lies a world that once flowed with water, where ancient oceans may have stretched across its surface, where life may have once taken root. To reach Mars is to stand at the doorway of two great questions. Could life exist beyond Earth? And could humans one day thrive here? The first step onto Martian soil wouldn't just mark the beginning of planetary exploration. It would signal the beginning of our evolution as a multi-planetary species. And while the journey may take only months, the meaning of that journey stretches across the entire span of human history. Mars isn't just in reach. It's our next great chapter, waiting patiently in the red twilight of space. Reaching Mars isn't a straight line. It's a dance of orbital alignment. We explore how the perfect moment can cut months off our journey, and how missing it could add years. In space travel, timing isn't just important, it's everything. As Earth and Mars race around the Sun at different speeds, the distance between them is constantly changing. There are moments when the two planets line up in just the right way, creating a kind of cosmic doorway. If a spacecraft is launched during this exact window, it can glide efficiently along a curved path called a Hohmann transfer orbit, using minimal fuel, while still gaining the maximum gravitational help from the sun. But if we miss this opening, the door closes and the opportunity vanishes for nearly 2 years. Think of Earth and Mars as two runners on separate tracks. Earth is on the inner lane moving faster. Mars is on the outer one moving slower. In order to catch Mars, we must leave Earth at exactly the moment when Mars is just ahead of us in its orbit. If we leave too late, we'll arrive where Mars was, not where it is. The universe doesn't wait for us. Its movements are exact, predictable, and don't care about our schedules. We must line ourselves up with the clockwork of the cosmos. These launch windows are figured out years ahead, down to the minute. Mission designers simulate planetary positions with powerful computers, predicting where Earth and Mars will be not just months from now, but decades or even centuries into the future. A launch mistimed by even a few days can need thousands of extra pounds of fuel, slowing the craft or causing it to miss Mars entirely and drift endlessly through space. But launch windows are only one part of the story. Gravity assists, or gravitational slingshots, let spacecraft steal energy from planets in motion. When a spacecraft flies close to a planet, it falls into its gravitational well, speeds up, and then exits on a different path with extra speed. This move doesn't cost fuel. Instead, it draws energy from the planet's own orbital momentum. The planet slows down ever so slightly, an unnoticeable fraction, but the spacecraft gains a big boost. The Voyager missions are perhaps the most famous example of this cosmic dance, thanks to a rare alignment of the outer planets that happens only once every 176 years. Voyager 1 and Voyager 2 were able to hop from Jupiter to Saturn, then onward to Uranus and Neptune, using each planet as a stepping stone. Without gravitational slingshots, such a mission would have taken decades longer and needed fuel tanks bigger than the spacecraft itself. This is the invisible art of space travel, riding the gravity of planets like a surfer rides a wave. Space isn't empty. It's filled with motion, with momentum, with energy waiting to be borrowed. By lining up our spacecraft with these forces, we transform the impossible into the achievable. Imagine watching Mars rise through the spacecraft window, not because we forced our way toward it, but because we let the universe carry us along its natural paths. Space exploration isn't about conquest. It's about working together with heavenly mechanics. The planets set the tempo. The sun keeps the rhythm, and we must learn to move in harmony with them. In the end, the question isn't just how far Mars is, but when Mars is where we need it to be. The journey to other worlds depends not only on technology, but on timing, waiting for gravity to open its hand and guide us forward through the grand and silent hallways of space. Between Mars and Jupiter lies a realm of ancient stone. It isn't the chaotic field of movies, but a sparse museum of planetary fragments. As we cross, we measure the time since the birth of the solar system itself. The asteroid belt stretches across hundreds of millions of miles, a vast ring of rocky remnants that once might have formed a planet. Instead, the huge gravitational pull of Jupiter stopped these fragments from ever coming together into a world. Today, they drift silently through space, relics from a time when our solar system was still forming unfinished pieces of a cosmic puzzle. As we cross this region, the journey becomes less about reaching a place and more about traveling back in time to witness the earliest building blocks of planets like Earth. Contrary to dramatic portrayals in science fiction, these asteroids aren't packed tightly together. Space between them is so vast that a spacecraft could pass through the belt without ever meeting a single rock. On average, objects within the asteroid belt are separated by hundreds of thousands of miles. In many ways, the greatest danger here isn't collision, but isolation. The silence is deep. There's no air, no wind, no sound, only the distant shimmer of ancient stones rotating slowly in the blackness, each one a witness to billions of years. As we travel deeper into this region, it becomes clear that the belt isn't a graveyard. It's a library. Each asteroid is a page in the story of planetary evolution, keeping minerals, metals, and ice unchanged since the dawn of our solar system. Some are rich in water locked within their minerals, offering potential resources for future missions. Others contain rare metals in amounts far greater than anything found on Earth. In the far future, humanity may look to this region for sustainable off-world mining, transforming these silent stones into stepping stones for interplanetary civilization. Time itself feels different here. There's no day or night, no rising or setting sun, only an unchanging view of stars. The only passage of time is the gradual shifting of the sun's light as our spacecraft continues its journey outward. In ancient times, the belt was a cradle of possibility. Now it's a quiet threshold, a boundary between the familiar inner planets and the vast, mysterious outer realms. We pass by Ceres, the largest object in the asteroid belt, once classified as a planet in its own right. At nearly 600 miles across, it's a dwarf planet with water ice beneath its crust and mysterious bright spots that reflect the light of the distant sun. Some scientists believe that beneath its surface could lie a hidden ocean, perhaps even the ingredients for life. Other asteroids, like Vesta, show signs of ancient volcanic activity, hinting at a time when these bodies weren't cold and dormant, but alive with internal fire. Crossing the asteroid belt is a journey that takes months, even at huge speeds. Yet, the true distance isn't measured in miles, but in moments of reflection. These drifting stones remind us that we're part of a changing system, one that has evolved, collided, and transformed over eons. Earth and Mars, Venus and Mercury, these planets are complete chapters. The asteroid belt is an unfinished sentence, a heavenly pause in the great story of our solar system. As we leave this region behind, we're no longer just travelers. We're historians of the cosmos, carrying with us the knowledge that every grain of dust here is older than life itself. Ahead of us lies Jupiter, the first of the gas giants, and with it, a new chapter of the journey, one not built of stone and silence, of storms and swirling clouds larger than entire worlds. Jupiter looms in the darkness, a world so huge it bends time around it. A journey here stretches our imagination of distance. What would it truly feel like to approach a planet deeper than all the oceans of Earth combined? As we leave the asteroid belt behind, the clock of our journey begins to tick differently. Every mile now places us deeper into the realm of Jupiter, the largest planet in our solar system and the ancient guardian of our cosmic neighborhood. Its presence is unmistakable. Long before we see Jupiter with our eyes, we feel it in the instruments aboard the spacecraft. Gravity begins to shift. Space itself seems to curve toward an unseen giant. This is no ordinary destination. This is a journey into the realm of Titans. Reaching Jupiter is a huge task. Depending on the path and technology used, a spacecraft can take anywhere from 13 months to nearly 6 years to arrive. For example, NASA's New Horizons probe, one of the fastest objects ever launched, reached Jupiter in just over a year. Meanwhile, other missions like Galileo and Juno took a longer route, using gravity assists from inner planets to gain the speed needed for precise orbital insertion. But regardless of the path, the moment of arrival is unlike any other in solar exploration. The instant when Jupiter's huge gravitational force takes hold, pulling the spacecraft into its sphere of influence. Jupiter contains more than twice the mass of all the other planets combined. It's not just a world. It's a failed star, a heavenly embryo that never gathered enough mass to start nuclear fusion. As we approach, its swirling bands of red, orange, and gold begin to fill our view. Its storms, some bigger than Earth itself, rotate with endless fury, powered by internal heat left over from its formation. Here, gravity isn't just a force, it's an experience. Time itself stretches slightly in Jupiter's presence. Seconds pass just a little differently, a subtle reminder that we're now under the influence of a planetary giant. In the darkness of space, Jupiter glows faintly from the heat rising within, unlike Earth, which warms itself with sunlight. Jupiter gives off more energy than it receives, powered by the slow gravitational squeezing of its massive body. As we draw closer, we see that its clouds don't drift calmly. They churn, they spiral, they rise and fall in huge waves, forming structures so vast they defy understanding. The Great Red Spot, a storm that has raged for centuries, spins like a blood-red eye watching the solar system unfold. The journey here isn't just measured in distance, but in awe. Our sense of scale begins to dissolve. Jupiter's diameter is 11 times that of Earth. Its magnetic field is 20,000 times stronger. If we could hear electromagnetic waves as sound, Jupiter would roar with an ancient cosmic thunder echoing across the void. And yet, despite its huge mass, Jupiter has no solid surface. To reach its center is to journey through layers of gas, liquid hydrogen, metallic hydrogen, each layer more extreme than the last, until matter itself becomes something alien and unknown. Even as we get close to the orbit of its moons, the journey continues. Europa, Ganymede, Io, and Callisto drift around Jupiter like miniature planets, each with their own secrets. Some are volcanic, some are icy, some may harbor oceans beneath their crusts. Oceans that could hold life in the dark. The time it takes to reach Jupiter isn't just a countdown. It's a transition from the familiar inner solar system to the vast, mysterious outer space where planets are no longer rocky worlds, but entire systems within themselves. To journey to Jupiter is to stand at the doorway of the great beyond. It marks the moment when our voyage is no longer just about exploration, but about meeting forces so great they reshape our understanding of what a planet can be. Here in the shadow of giants, time stretches, gravity deepens, and the universe reveals its true scale. No spacecraft truly visits the outer planets without first dancing around Jupiter's orbit. We explore how gravity itself becomes an engine, throwing us deeper into the void. Jupiter isn't just a destination, it's a gateway. Its huge gravitational pull acts as a cosmic slingshot, capable of speeding up spacecraft to speeds that would otherwise be impossible with fuel alone. As we approach this planetary giant, we're not just observers of its greatness, but participants in a heavenly move so elegant and powerful that it has allowed humanity to reach the farthest edges of our solar system. Using Jupiter's gravity isn't about fighting the planet's pull, but giving into it, letting gravity guide our path and transform our speed with the precision of an ancient clockwork. A gravity assist or slingshot move is one of the most clever strategies ever developed in space exploration. The idea is simple but deep. As a spacecraft gets close to Jupiter, it falls into its gravity well, speeding up as it's pulled toward the planet. Instead of crashing into the massive sphere, it curves behind Jupiter, catching a fraction of the planet's forward momentum as it orbits the Sun. This exchange is subtle, unnoticeable to Jupiter, but huge to the spacecraft. With no fuel used, the spacecraft is suddenly traveling faster, pushed outward on a new path, often towards Saturn, Uranus, Neptune, or even beyond the edge of the solar system itself. This method was famously used by both Voyager 1 and Voyager 2. Launched in 1977, these spacecraft were designed to take advantage of a rare planetary alignment that happens only once every 176 years. By exactly timing their journey and using Jupiter's gravity, they gained enough speed to visit all 4 outer planets in a single mission. Without the slingshot effect, reaching Neptune alone would have taken more than 30 years. Gravity became a silent engine, one that needed no fuel, no maintenance, and has continued to push Voyager 1 into interstellar space, where it now travels among the stars. As our spacecraft gets ready for this move, every movement must be figured out with extraordinary precision. If we pass too close to Jupiter, the intense radiation belts could damage or destroy the spacecraft's instruments. If we pass too far, we won't gain enough speed. The ideal path is razor thin, measured in millimeters over millions of miles. Here, timing isn't just important, it's absolute. The universe gives us a single chance to catch Jupiter's momentum. Miss it and the journey may be delayed by decades. experience of using Jupiter's gravity is unlike any other. From our viewpoint inside the craft, the giant planet grows rapidly in the window. Its swirling clouds stretching across our entire field of view. We feel the gravitational pull increase. Even though gravity can't be felt directly, its effects on acceleration become clear. Our onboard clocks begin to tick slightly slower due to time dilation caused by Jupiter's huge mass. We're not simply moving through space. We're moving through the shapes of space-time itself. As the spacecraft swings behind the planet, Jupiter fills half the sky, glowing with storms that have raged for centuries. In that moment, we're suspended between two forces, the pull of Jupiter and the forward motion of its orbit. Then, with silent precision, we're flung outward. Our speed multiplies. Our path shifts. We're now no longer just visitors to the outer solar system. We're travelers of the deep beyond. Using Jupiter's gravity is a reminder that space travel isn't a battle against nature. It's a partnership with it. We don't conquer the cosmos by force, but by learning its rhythms, its patterns, its hidden pathways. Jupiter, the ancient king of planets, becomes our ally, opening the door to the solar system's farthest frontiers and sending us onward toward the ice giants, the frozen moons, and secrets waiting in the darkness ahead. We draw closer to the great red spot, an endless storm bigger than our entire world. As the hours add up, we wonder how long does it take not just to reach Jupiter, but to understand it. As our spacecraft settles into orbit around Jupiter, we enter the presence of one of the most lasting wonders of the solar system. The Great Red Spot isn't just a storm. It's a planetary monument to time itself. This huge vortex has raged for at least 350 years, possibly far longer, swirling relentlessly within the planet's dense atmosphere. If Earth's fiercest hurricanes last days or weeks, the Great Red Spot is their ancient ancestor, spinning across centuries, untouched by landfall, uninterrupted by oceans, constantly fueled by the heat radiating from deep within Jupiter's core. From our viewpoint, high above Jupiter's cloud tops, the storm appears as an enormous oval colored in muted crimson and copper, circled by bands of white and tan that stretch around the planet like stripes on an infinite canvas. Lightning flashes silently in the swirling clouds, some bolts so powerful they could light up entire cities. Winds scream at speeds over 400 mph, faster than any storm ever recorded on Earth. And yet, in the stillness of space, we hear nothing. The storm is silent, its fury shown only in motion. The Great Red Spot is so big that 2 or even 3 Earths could fit inside it. Observations across decades have shown that the storm is slowly shrinking, becoming taller and more circular as it ages. Some scientists wonder, is the Great Red Spot dying? Or is it changing, getting ready to transform into something we can't yet imagine? A storm that lasts centuries, may be as brief as a raindrop in Jupiter's vast atmospheric cycle. As we study the storm, instruments detect that it extends deep below the visible cloud tops, possibly hundreds of miles into the planet's interior. Unlike storms on Earth, which are powered by the sun's energy, Jupiter's storms are driven by internal heat. The planet is still shrinking under its own gravity, releasing energy that fuels atmospheric motion from the inside out. The Great Red Spot isn't just a weather system. It's a window into Jupiter's living, breathing interior. We observe how surrounding jet streams swirl around the storm, feeding it with continuous energy. Huge ammonia clouds rise and fall like ocean waves, while vortices spin off the storm's edges, only to be pulled back into the main vortex. The storm appears eternal, but it's constantly changing, its boundaries rippling like the edge of a flame. To truly understand the Great Red Spot is to accept the vastness of planetary time. On Earth, we measure time by hours, days, and years. On Jupiter, we measure it by storms that span generations. Storms that were raging before telescopes were invented, before electricity was discovered, before modern nations were born. To imagine standing above the storm is to imagine watching not just weather, but history itself in motion. The red spot forces us to ask deep questions. What does it mean for a storm to live longer than civilizations? What can we learn from a world where the weather is measured not in forecast cycles, but in eras? As we drift past the storm, its presence stays in our minds long after it fades from view, not just as a swirling storm, but as a symbol of time beyond human understanding. We leave Jupiter's orbit with a new understanding. In the grand scale of the universe, even storms aren't events. They're eras. And this, the storm that has lasted centuries, is a reminder that some forces of nature aren't just experienced, they're endured. Farther still, Saturn rises like a dream carved from ice and light. Its rings stretch wider than Earth itself. Reaching this world tests the limits of time and human patience. As we leave the gravitational hold of Jupiter, our spacecraft continues onward, journeying through a realm where sunlight is fading into a pale, distant glow. The darkness deepens, but ahead, something luminous begins to appear. A delicate, shimmering halo suspended in space. Saturn, the jewel of the solar system, slowly shows itself. Unlike any other planet, its beauty is immediate, undeniable, and otherworldly. The rings, made of countless pieces of ice and rock, catch the faint light of the sun and scatter it in all directions, creating a cosmic crown that sparkles like frozen fire. Reaching Saturn takes time, years, not months. The fastest spacecraft ever sent to Saturn, NASA's Cassini, took nearly 7 years to arrive. Yet, every day of travel is rewarded the moment Saturn comes into view. While Jupiter is massive and commanding, Saturn is graceful and mysterious, a planet of golden shades, wrapped in veils of methane clouds, and circled by rings that stretch up to 175,000 miles from edge to edge. Despite their grandeur, these rings are incredibly thin, no thicker than a few dozen feet in many places. A planetary masterpiece carved with precision by gravity, time, and the slow dance of orbital mechanics. As our spacecraft approaches, we begin to see the details that make Saturn so captivating. The rings aren't solid. They're made of billions of individual pieces, ranging from grains of sand to chunks the size of mountains, all orbiting Saturn in perfect harmony. Each particle follows its own path, yet together they create a structure so organized it looks almost intentional. The gaps between the rings, like the Cassini division, are carved by the gravitational pull of Saturn's moons, which act as shepherds, keeping the rings in place and preventing them from spreading out or collapsing inward. Time on Saturn moves to a different rhythm. A day here lasts just over 10 hours, making it one of the fastest spinning planets in the solar system. This rapid rotation causes Saturn to bulge at its equator, giving it a slightly flattened appearance. Yet a year on Saturn lasts nearly 30 Earth years. Seasons here stretch across decades, slowly shifting as the planet tilts on its axis, casting its rings in shadow or bathing them in light. The atmosphere of Saturn is similar to Jupiter's, mostly hydrogen and helium, but with a softer, more subdued appearance. Instead of Jupiter's bold bands and violent storms, Saturn's clouds flow in gentle pastel shades of gold, amber, and cream. Yet beneath this calm exterior lies tremendous power. Winds on Saturn can reach speeds of over 1,100 mph, faster than anywhere else in the solar system. Deep within the planet's atmosphere, lightning storms rage with energy thousands of times more powerful than those on Earth. Radio emissions crackle through space, creating what scientists call whistlers, ghostly sounds that echo through Saturn's magnetic field. But Saturn's greatest mystery lies in its moons. Over 80 moons orbit the ringed planet, each one a world unto itself. Titan, the largest, is bigger than Mercury and has a thick, nitrogen-rich atmosphere. Its surface is hidden beneath orange haze, but beneath that haze lie lakes and rivers, not of water, but of liquid methane and ethane. Titan is the only moon in the solar system with a substantial atmosphere, making it one of the most Earth-like worlds we've found, despite being hundreds of millions of miles away and cold beyond imagining. Then there's Enceladus, a small icy moon that hides a liquid ocean beneath its frozen crust. Geysers of water vapor shoot from cracks in its surface, spraying ice particles into space. Some of these particles fall back to the surface, but others join Saturn's rings, constantly refreshing them with new material. Scientists believe that beneath Enceladus's ice lies a warm ocean heated by tidal forces, an ocean that may contain the conditions necessary for life. To reach Saturn is to reach a place where possibilities expand, where time slows, where beauty and science merge, where every discovery raises new questions. The journey to Saturn takes years. The wait is long. The distance is vast. But when the rings finally appear in the spacecraft window, glowing softly against the blackness, every moment of travel feels worth it. Saturn doesn't demand attention like Jupiter. It invites contemplation. It whispers rather than roars. And in that quiet elegance, it teaches us that some of the most profound wonders in the universe are also the most delicate. As we orbit Saturn, watching its rings rotate slowly beneath us, we understand that this isn't just a planet. It's a work of art, a reminder that the cosmos creates beauty not through chaos alone, but through balance, precision, and time. Beyond Saturn lie the ice giants, Uranus and Neptune, worlds so distant that sunlight arrives as a whisper. To journey here is to measure time not in years, but in decades of patient waiting. As we depart Saturn's rings and venture deeper into the outer solar system, the sun becomes little more than a bright star. The warmth and light that once defined our journey fade into a cold, distant glow. Here, in this frozen realm, we find Uranus and Neptune, two planets so remote that they were unknown to ancient astronomers and invisible to the naked eye. Reaching Uranus takes roughly 8 to 9 years using current spacecraft technology. NASA's Voyager 2 remains the only spacecraft to have visited this distant world, arriving in 1986 after a journey that began in 1977. What it found was a planet unlike any other. Uranus is tilted on its side, rotating at an angle of 98 degrees. This means that instead of spinning like a top, it rolls through space like a ball, with its poles taking turns facing the sun. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. Imagine a world where summer and winter each last a human lifetime, where the sun doesn't rise and set daily, but hovers near the horizon for decades before sinking into an equally long night. The atmosphere of Uranus is a pale blue-green, colored by methane gas that absorbs red light and reflects blue. Unlike the dramatic storms of Jupiter and Saturn, Uranus appears calm, almost featureless. But this calm is deceptive. Beneath the visible cloud layers, winds rage at hundreds of miles per hour, and temperatures plunge to nearly 370 degrees F, making it one of the coldest planets in the solar system. Uranus has 13 known rings, much darker and narrower than Saturn's, and 27 moons, many named after characters from Shakespeare and Alexander Pope. The largest moon, Titania, is scarred with massive canyons and fault lines, evidence of a violent past when the moon's interior froze and expanded, cracking the surface like ice on a frozen lake. But the true challenge lies in reaching Neptune, the farthest planet from the sun. The journey takes between 12 and 14 years. Voyager 2 reached Neptune in 1989, completing a grand tour of the outer planets that remains one of humanity's greatest achievements in exploration. Neptune is a world of deep blue, its color more vivid than Uranus due to an unknown atmospheric component that scientists are still trying to understand. Despite being nearly 2.8 billion miles from the sun, Neptune is surprisingly active. It has the fastest winds in the solar system, reaching speeds of over 1,200 mph, and massive storm systems that appear and disappear over the course of years. The Great Dark Spot, observed by Voyager 2, was a storm system nearly the size of Earth, spinning counterclockwise in Neptune's southern hemisphere. By the time the Hubble Space Telescope looked at Neptune a few years later, the storm had vanished, replaced by new systems elsewhere on the planet. Neptune's largest moon, Triton, is one of the strangest objects in the solar system. It orbits Neptune backward, suggesting it was captured from the Kuiper belt rather than forming alongside the planet. Triton's surface is covered in frozen nitrogen, and geysers erupt from beneath, shooting plumes of nitrogen gas miles into space. Despite temperatures of 390 degrees F, Triton shows signs of geological activity, making it one of the most intriguing targets for future exploration. To reach these ice giants is to journey to the edge of what we consider the planetary system. Beyond Neptune lies the Kuiper belt, a vast ring of icy bodies and dwarf planets, including Pluto. Beyond that is the heliopause, the boundary where the sun's influence fades and interstellar space begins. The journey to Uranus and Neptune tests not just technology, but human patience and vision. Missions to these worlds require decades of planning, years of travel, and generations of scientists to see them through. Yet the knowledge gained from these distant voyages expands our understanding of planetary formation, atmospheric dynamics, and the diversity of worlds that exist in our solar system. As we contemplate the ice giants, we realize that the question isn't just how long it takes to reach them, but whether we're willing to invest the time, resources, and imagination required to continue exploring the farthest frontiers of our cosmic neighborhood. For now, Uranus and Neptune remain distant, cold, and mysterious. But they remind us that the solar system is vast, that there are still worlds waiting to be explored, and that the human spirit is capable of reaching even the most distant and inhospitable places in search of understanding. And so, as our journey draws toward its end, we find ourselves not at a conclusion, but at a beginning of questions that may take centuries to answer, and mysteries that may take millennia to solve. The voyage to the outer planets isn't just about distance. It's about time, patience, and the enduring human desire to see what lies beyond the horizon, no matter how far that horizon may be.